I'm really sorry about that, starting early there, prematurely. It doesn't usually happen to me. Promise. High-performance web platform. How many people are web developers here? How many people have used more than one browser? How many Chrome users do we have here? And how many Firefox users? I won't even ask about my company. So today I'm going to be talking about browsers. I'm a bit of a browser nerd. I worked for sort of evangelism for Internet Explorer for a while, for quite some time. But all the time during Microsoft, I've been involved in C#, JavaScript, and browser evangelism. And kind of this is the stuff I've learned about browsers from a browser point of view about web development, and thinking about how we develop really high-performance applications for the web, and also for native applications which potentially use JavaScript. And so we're going to look at the kind of constraints on performance of mobile applications and web applications. We're going to look at how browsers actually work internally. And then from that, we'll then figure out, well, what can we do as developers to actually improve the performance inside browsers based upon the knowledge that we've gained about the way that browsers actually work. So constraints are probably the most important thing to consider when you're a web developer. And you probably already do this because, you know, network, how much is passed over the wire. These things will be really common to you when you're thinking about developing websites. You don't want your images too large. And there's lots of things which are really obvious about performance, which you can do. But performance is becoming really, really important in web development. And that's because it's gone are the days, we had this little peak, I guess, where desktop computers were slow to start with, and we were all using perhaps 486s and really crappy processors, very little graphics cards. And then we had really powerful desktop machines. They started getting more and more powerful. Then we had laptops, which were, you know, portable and powerful. And then we had this real weird dip where we went from these computers, which had lots of power, were always connected, to then mobile phones, which were, in their first incarnation, slower, and, you know, half on, half off, sometimes on, sometimes tell you they have connection, but actually they completely don't. You know, it's a completely different way of getting the internet and working with the internet. And those constraints, those physical constraints, affect how fast we can serve websites or web applications. And so in terms of network, the most common kind of problems that people would say would be, well, bandwidth. Because the amount of bandwidth that you have, so if you're on a 4G network or a 3G network on your phone, or maybe you've got an ISDN connection or an ADSL connection or whatever. I have a 50 meg broadband connection at home in my office. You know, but then when I work in remote sites, I might be down to 10 meg. And that massively impairs, of course, the way that you're able to use a website. But bandwidth's only really one portion of it. Bandwidth's the thing that ISPs, Virgin Media, will tell you is really important. Oh, you've got 50 megabits per second. That's really fast. But actually, latency is far more important. And an ISP never really publishes latency information about how fast their network is. And also, there's latency between the actual website and then the servers which host that website. So it doesn't really matter how big the pipe is. It really also matters how long that pipe is as well. How much data you can get through the pipe is one thing, but also how far that data has to travel, because nothing can travel faster than the speed of light. Yet. And then there's the other constraint of people's data plans on mobile phones. You know, you want to be cognizant of the fact that maybe we get 4G. I'm actually streaming to this via my mobile phone because I couldn't get onto the network here. So, you know, I've got 4G. It's very, very fast, but I do have a data plan, and someone's got to pick up the bill for that thing. Not me, Bill Gates, but never mind. He's got a laugh. And there's lots of studies which show like the different speeds that you get in terms of bandwidth across megabits per second across different types of Wi-Fi or 4G. But in reality, as soon as you start getting around the Wi-Fi level, 5 megabits per second, doesn't really matter necessarily if you have 50 megabits per second. You're not going to really load sites any faster than anyone else because of latency. It's actually, there's a big cap, a big drop-off on performance and increase of having really powerful, really huge bandwidth. Maybe it's good for file transfer protocols and stuff, but actual general browsing of the web, there's very little difference or noticeable difference between some of these things because of the latency that's involved in the network which serves websites and serves systems. So it's important for us as developers to consider this and think about not only performance, not only bandwidth, not only latency, but the perceived performance of these connections. So if we look at a trace from a website, it might actually take 1.18 seconds to load the entire thing, the entire website. But actually, the time to glass in terms of the time that the user got to the URL and there was something on the glass on the screen. We call it glass. It's not always glass, obviously, but there's something on the screen that is usable and they can start interacting with. On this particular website, that's 0.65 seconds. So the perceived performance of this page is 0.65 seconds because the user doesn't necessarily know that there's other stuff happening and loading in the screen. Poorly perceived, like with bad perceived performance, your site will be perceived to take 1.81 seconds. But if you're clever about the way that you show content when it's ready, you can get that down to far shorter amounts. So if you go to Google, for example, or Bing, which they really care about how fast that first page loads, and they do all sorts of tricks to get it work really, really fast. That particular page, they do a lot of this, where they're doing a lot of stuff, loading lots of other features that Google does, which are auxiliary features for the application, but they're loading that search box as quickly as they possibly can, because that's probably what you're going to want to be able to do in that application. That's what you've got to think about when you're building applications. Loading the things that your user, the central function of your application, needs to be available first, and then auxiliary functionality needs to come second. Now, actually, if we look at this performance trace, the actual page load time was 1.81 seconds, but there's a CPU time, the amount of time which was processing in that application, which was 1.39 seconds. Which means there's a delta between CPU time and load page time, which means there's an idle time of the CPU. There's time when the CPU was doing nothing of 0.42 seconds, and that is where we could potentially improve our performance if we think about things and we think about the ways that we can manage performance in an application. So you can save quite a considerable amount of time, and that time is effectively money, especially if you're selling for your website or that is a service to your company. So making sure performance is a really important part of your application. Now, another thing that's really important in web applications, but it's almost entirely missed by web developers, and never really missed by application developers and desktop developers, is memory. Very, very few web developers I speak to realize the kind of memory implications that their websites might have. They don't know the memory payload of their application. And because you don't really think about it when you're doing web dev, you don't really think when you add an image to a site, you don't really realize that that adds to the memory of that particular page, that application. When you're adding JavaScript frameworks, you don't realize that that's adding to your memory load of that application. And so this is a chart of the top 5,000 sites in the world. And many of them are using, say, 20 megabytes of data. And there's quite a few which are doing that. And then it goes up, and then 40 megs, 60 megs, 80 megs. Right up to the top here, where there's some sites using over 200 megabytes of data, of memory, in-memory process, just trying to serve that one particular website. It's actually a government website in the US which does this, which is 200 megabytes. And it's just an informational site. It's not a particularly, it's not a site which has, it's not Gmail or anything like that. This is just poor performance practices which have led them to that kind of world. So you may be thinking, well, the average sites, they're using under 20 megs, that's pretty reasonable in terms of a website, surely. But you've got to remember that most people don't just have one tab open in their browser, they have like 20. We actually did some research. The average number of tabs open in a browser is 3. If you think about your web usage, how many of you use more than 3 tabs in your browser at one time? That's the problem with averages, you see. If a guy's got his head in the oven and his feet in the freezer, on average, he's comfortable. But there are people at the extremes. We are the people at the extremes of web technology because we care about the web. We use the web consistently, constantly. We'll have 20, 30, we don't care, tabs open at a time. And the way that browsers handle memory is each tab has memory allocated to that tab. And every time you switch between tabs, if you had, say, 20 200 megabyte websites open, you would eventually run out of memory on that device. So you have to cache it to disk. You have to take the memory heap, you put it to disk, and you keep doing that. And as you switch between tabs, as you're doing multiple working, because you're all very productive people, you're thrashing the hard drive. You can actually reduce the hard drive, the storage system on SSD or Rust disk of like a couple of years just by thrashing it. Poor memory management in applications. Desktop developers know these things. It's quite common knowledge when you're an application developer to manage your own memory. But in web development, it's really not. Most people don't even think about it. The other one is power consumption in terms of how much power you're going to be using in your application. I'm using a tool here which looks at a thing called vsyncs in the browser, which is the synchronization points at which we're able to paint to the screen. So if you've got a monitor on your hardware, it actually has a specific hard, there's a hard number of how often it can paint the screen, like 60 megahertz or 50 megahertz or whatever it is. And that sends an interrupt to the operating system to say, look, I can be painted on. And then the operating system paints to that screen. Applications like Internet Explorer and Chrome and Safari look at that number, that sync, and that's when they paint data to the screen. And so what you're wanting to try and do is try and make sure that you're doing things like your JavaScript and your paints are aligned as close as possible to those vsyncs. Now, you're not going to be able to do that as developers, web developers, but if you use things like set timeout in JavaScript rather than request animation frame knows about vsyncs. It will only signal that there's something that you can paint when a vsync's available. Something like set animation timeout is just run on 60 milliseconds or 100 milliseconds. It has no idea about vsyncs, so you'll be generating draws which it can't process and paint. All that time is wasted. Also, when you load an application, it's really advisable just to let it all rest. If you have an animation, especially which is dependent on JavaScript, running as soon as the application runs, the browser can't do anything to manage this process. However, if you just load content and then let the thing settle, let the application settle, browsers like Internet Explorer, and we have this a new feature in IE11, we can determine that there actually isn't anything needed to do on the GPU because they're just scrolling the site and reading it. They're not doing anything on the site. We recognize the DOM's not being interrupted. We can actually switch vsyncs off on the system and save power, which doesn't sound like a lot, but if every website in the world did that, that would mean that batteries on phones would last tons, like amazingly longer in terms of what they currently do. So we're trying to do as well as we can in the browser to make power consumption really a first-class citizen, thinking about power consumption every time we do paints to the screen. And it's just interesting if web developers try and think about these things as well. Memory, network, and power are really the three key things that you need to think about as a web developer for performance. And this is on the web, and also when you're developing applications in Cordova, or you're doing anything, if you're even doing iOS development or anything, you'll always be wanting to think about those three things. Yeah.
What is the alternative to the set timeout function?
Request animation frame is one example of that, where we see request animation frame instead of request timeout, instead of set timeout. Power consumption is really important on mobile phones. Because if you think about it, a modern mobile phone can safely sort of disperse, say, 5 watts of power. And if it's running a browser and the operating system, you're probably at 2 or 3 watts of power already. It's like at that level of capacity. Then let's say if you developed a web application, which is a bit like Google Maps, and you needed to go and get the networks. You need to go and get information from the network, like you needed to get tiles, image tiles for your map. Well, OK, you're going to add the Wi-Fi stack needs to be integrated, or the GPRS stack needs to go and get that stuff. So that's probably another watt of energy. That piece of hardware has to be switched on that phone. And then you need to maybe do some complex processing. You take the images down, you stitch them together, you're scrolling a lot, the GPU starts having to kick in. So the GPU's on as well, and that's doing its work. And maybe if it's a dual-core phone that's going to have a second core in the CPU is going to kick up as well to try and help you with that image decoding and stuff. Before you know it, you're at that 5-watt maximum of that phone's capability. And what happens? Well, the phone starts getting hot. When the phone starts getting hot, the phone has to do a thing called thermal mitigation, which is like, I'm too hot, stop! So it stops doing stuff, it slows down, and one of the first things that will slow down could really interrupt Google Maps or something like that. Because let's say this was a Google Maps sat-nav application, and you've got it on your sideboard, and it's doing GPRS, it's doing GPU, it's got a couple of cores open, it's running hot. And if you've ever run sat-navs on your phone, you'll know they're hot, they're always hot. And you start draining battery because it's really hot. There's physics in this thing. You have to apply more power to run the whole thing. So what would you do if you're running out of battery, you're low on battery, you're in your car, you're close to your thing? What's the thing that you would do? You're not plugged in at the moment. What are you going to do? You're going to reach for the car charger and plug your phone in and start charging it. But have you ever noticed that when you do that on sat-navs, it doesn't ever seem to work and you still run out of battery? That's because thermal mitigation is kicked in, and the first thing that a phone switches off is the capability to charge, because it will say, if you charge me, I'm going to get even hotter. So I'm not going to do that. So your phone will eventually run out of battery and die. Even though it's plugged in and you think it's charging, it's not charging because it doesn't want to charge because it's already too hot. It's things like this we have to think about when we're developing web applications. Power consumption is really important. People will stop using your site, maybe not, will stop using your app, probably, if they think that it drains their battery. Specifically on Android, because you can see this stuff really easily on Android, how well an application is draining your battery. Anyway, but when we think about performance, it's not just about being fast, it's also about being efficient. You need to think as web developers the fact that stuff is going to be on desktop, stuff is on mobile, and it's on tablets, and the physical constraints on those devices are different. And it's not just about whether the screen looks good on those devices, it's about whether it performs well as well. One of the key aspects of this, if you want to figure out, well, what do I need to focus on, is looking at analytics. Implementing analytics in your application, not just Google Analytics to figure out how your users are doing and what devices they're using, which will help in knowing the devices they're using, but also trying to analyze, well, what are they doing in terms of where are they going on the website? What are the hot paths of my website? What application features are they using and what ones are they not using? And optimizing and tweaking performance to make those really efficient is probably the best place. Because just trying to make it faster without knowing the problem or the hot paths is going to cause you difficulty. So let's look a little bit at how a browser works. And I don't really know how Chrome works or Safari, but I've been informed that it's exactly the same in terms of pipeline as IE. And this is the kind of very dumbed down version of how a browser takes a network request and converts it to the screen. And this is I'm pretty sure, although I've never been told I'm wrong. So, and I've presented it to Google developers before, and they've never pulled me up on it. But this is, I believe, the pipe flow for every browser pretty much out there, where you get a network request, and there might be more than one. A browser, there's limited to how many requests we can make asynchronously in a browser. I think it's 5 requests we can make at the same time, and then everything else has to queue up. So you're waiting on certain requests. So the obvious way of reducing or increasing asynchronicity is making sure that you only have 5 HTTP requests in a web page, which is unlikely you'll ever be able to get to that. But it's being able to, other than that, they're going to have to start queuing and stuff. So networking is a really important aspect of the pipeline. So someone puts a URL in, we go to that URL, we do DNS, TCP, all that sort of stuff. We get all of the files that we need, and we start parsing them. We start understanding, well, what does this HTML content look like? Okay, there's some CSS information, there's some JavaScript files that I need. Go off on the network and start gating those things as well. And it calls back to from the networking cache, it calls back, the parsers call back to the networking cache, makes subsequent network requests. On average, I think there's something like 45 requests of most applications have on that process where they're getting new information. Some browsers will do things like, they'll do some intelligent guessing of what you might go to next, your next page. So it's not just loading the content and networking of the current page, but also what the user might go to next in terms of preloading, DNS resolving and stuff. So Google, for example, if you go to the Google website and you do a search, they might pre-cache the DNS lookups for the first 3 items that are in that list because they know you're likely to go to those. I don't know if that's exactly what Google do, but they'll do some stuff like DNS prefetching and prefetching of content potentially. If they know, it's highly probable you're going to go to one of the sites which it recommends or the links off of that other site. So they'll pass that information. We then, from that information, can understand the HTML structure of the document, and we can create a thing called a DOM tree. So this is the thing that you interact with in JavaScript. It's a node, different nodes of elements which are related in a tree. No styling information on this at all. It's just the structure of the application as it stands in terms of a DOM tree. We then take all of the CSS, which is in the application, when we cascade that. So we figure out, well, what should this element be? Like, CSS is very complicated, the whole cascade. It's very difficult to compute. So there's lots of computation which is happening at that point. We then also load all of the JavaScript into the application. And JavaScript lives in a sandbox. It's unable to communicate with any other aspect of the system apart from if it calls into DOM APIs. This is interesting. JavaScript is probably one of the areas where we've had the most progression in performance over the last 2-3 years. first starting off with the V8 engine and like Chrome's development of the V8 engine. And what Chrome's V8, the reason why it's so fast, I guess, there's lots of performance things that they're doing in JavaScript, but JavaScript is fundamentally a dynamic language. And what V8 really does is remove some of that dynamicness from it by jitting. So it will create real classes for objects and get some of the performance gains that you'll get from class-based languages and apply that to dynamic languages. So we can start seeing JavaScript performance improve or get closer to native performance. Which means that depending on what you do with JavaScript, if you create properties or delete properties, then they have to delete the class structures which represent those properties. So there's things that you can do by accident in JavaScript which actually messes up the performance gains that you get with things like V8 and Chakra, which is our version of the JavaScript engine. So that's a completely different talk about how you can ruin your JavaScript to make it really badly perform on V8. But it's worth noting that they're doing some really clever things. JavaScript engines today are doing really clever things. And Mozilla are kind of pushing this space as well with a thing called ASM.js, which we've just announced support for with Internet Explorer as well, which compiles, ahead of time compiles JavaScript. So stops it being dynamic and ahead of time compiles JavaScript. And takes that to performance levels which are C++ as fast as, near as damn it, as fast as C++. You won't potentially be using this for your average website, but if you were compiling a Unity game or you had some thing where you needed to use JavaScript as a runtime, it needs to run in the browser, but you want to take a C++ application and convert it into JavaScript, you might use ASM.js. So JavaScript's really interesting. We're getting really fast with JavaScript. It's not the language it used to be because of V8, because of Chakra, because of things like ASM.js. JavaScript can be very, very, very fast, and it's getting faster all the time. What's interesting, though, the DOM's not very fast, and no browser's really fixed that. There's not really much stuff which has happened in the DOM. So you have companies like Facebook creating virtual DOMs with React.js to try and get round of the DOM problems. But I guarantee that this is a serious focus for browser developers at the moment, thinking, well, how do we make the DOM faster? And I know at least our team is working really heavily on making the DOM much, much faster to work with. So anyway, we've got all the JavaScript, we've got the CSS. The JavaScript can change the CSS, it can change the DOM. But we've got all these things we can start thinking about formatting. Well, what objects are what colors? Well, where are they positioned on the screen? And we can start laying them out on the screen as well. And in Internet Explorer's version, we're laying out everything out as a rectangle on the screen. Okay, so that object's over here, it's at this particular pixel. Whether or not you use margins or autos or percentages, at the end of the day, we're working out as rectangles in pixels, which we're going to draw to a screen somewhere. We lay out all the rectangles, the surfaces, if you will. And then we get a thing called a display tree, which is it's a bit like the DOM tree, plus the CSS, plus your layout systems, all ready. And we say, OK, we're ready now for painting. But the display tree can't just paint. It has to wait for that monitor, for that vsync from the monitor. The monitor says, I'm ready to paint. And when it's ready to paint, we can put a display tree. Take that display tree, pass it over to the GPU, and it will be displayed on screen. And obviously, this stuff happens in milliseconds, and it changes constantly. If you're editing the DOM APIs here, you might have display trees which are then corrupted, which we can't paint. So the more work that ideally, if you could just go through this pipeline once, which is never possible, obviously, in web development, but if you could go through this pipeline once and you had a display tree, it would be a really efficient website. Where it won't be efficient is if you're changing the CSS and DOM and JavaScript on the fly, constantly altering the DOM, making things hover, disappear, hide, altering the system. We're constantly throwing away the display tree between paints. So we're really inefficient, I guess. So you're trying to do as little as possible to the document, really, in its process. The only things that you want to be doing to a document are the things which help users complete their task and do their job. So if you've got an animation for an ad, which is on a set timeout JavaScript loop, and it's constantly running, you're constantly having to repaint the screen, even though the actual application might not have changed at all. So it's just important to remember ad networks are really often one of the common problems with this. Is they stuff JavaScript into your application that you have no control over, and it can really affect performance. So the system has a vsync, and it says, OK, I want to paint something to the screen. So it goes to the display tree, the application. So I've got a display tree, here it is, and it starts painting that. So it's taking all of the individual rectangles and it starts painting on them. We call that, the process in Internet Explorer uses DirectX, which is a system-level API, which paints those little surfaces in DirectX. The same thing that we use in games and we use in applications and stuff. It's just DirectX which does all of that. So this loop is constant. Things happening, the user interacts with something, it presses a click button, it changes a DOM API, it's constantly iterating over this stuff. There's only one thing outside of the pipeline, and this really only happens, I think, in Internet Explorer, which doesn't affect the pipeline, but has a user input, and that's pinch and zoom. And I'll show you a little bit how this works. It's called, we call this direct manipulation. So hit testing and direct, so input like mouses and things are probably going to have an effect on the DOM APIs and potentially refactor the display tree. But there's a really nice little feature that the IE team added for pinch and zoom to make it really efficient. And you can see it in work when you look just slightly at a website. And I'll take this website, for example, which is called status.modern.ie. This is the roadmap for Internet Explorer, but it's completely irrelevant. I could have chosen any website. However, I wanted you to know that we have a roadmap for Internet Explorer. If you're interested on the features and capabilities like ASM.js, which is coming out, or some of the newer kind of things that we're working on, you can see here exactly what we're going to be implementing in IE 12, IE 13, and beyond. But it's an example of, I'm on my Surface, it's a touchscreen device. Oh, sorry, there's a little bit of the latency for some reason. So I'm on my Surface, you'll see I'm scrolling up and down on the screen. And you'll see I zoom and pinch zoom. And you see how, you might not be able to see this at the back, but how jaggy the text is. And then I let go of the screen, and the text becomes extremely crisp. That's because when I'm actually manipulating the scroll, what's happening there is that I'm manipulating a bitmap on the GPU. And then when I let go, we do the whole display tree thing again. So when I'm scrolling and manipulating the screen and moving it around, really, in reality, what I'm doing is I'm moving a bitmap on the graphical processing unit of that computer. I'm not going back through that pipeline and relaying out stuff. The relayout happens when I let go of the screen, when I'm happy with the zoom level. And the reason for that is obviously, if you imagine, if you're zooming, we'd have to repaint the screen and recalculate everything every time we got an input change on the scroll and zoom. So the way we get around that is by using the hardware acceleration of the platform. And basically, the reason that's jaggy is because all you're doing is zooming in a bitmap until you let go. It's just important to remember. Now, that for most purposes, that's good enough because that bitmap gives you an idea of how much you're scrolling. But when you let go, it gives the full composite render. Yeah.
How does that work if you've got any kind of media queries or sort of
so
zoom-based things? I mean, is there a way to detect whether the browser's going to have that behavior?
Well, every browser has that behavior. It's just depending on I only know the way we implemented it. We're doing it on the GPU. Some other browsers will implement the exact same feature on the CPU. But until you zoom in and zoom out, that wouldn't affect a media query because your meta width is exactly the same, potentially. So you might disable streaming, and that wouldn't happen as well. You can do that. So it wouldn't affect a media query, effectively. So that's the kind of pipeline that it goes through and how we produce things. And you'll see that there's lots of points in there where there's lots of bottlenecks, lots of consequences, lots of things that are very complicated and under the hood magic that browser developers are doing, which means that we have to think about things quite heavily when we're web developers to think, well, what can we do to make websites fast? And it's important because here's some stats from Google that they said that they put in artificial sleeps in their application to slow it down by 500 milliseconds, Google's applications. And they noticed a 20% drop in usage of that application. So, that's 20% people not using, say, Google search because they added a 500 millisecond delay. I think if anyone's from the Bing team, they should probably be looking at this and say, well, if we just slowed Google down by 3 seconds, we could get some more users. But it's really important for people like Google to be very, very fast. An actual 500 milliseconds might not sound like a lot, but it's an awful lot in performance terms. Amazon, they've calculated somehow, and this is by using analytics, which is really important to understand how your application works. They recognize that the slower their application is, by 100 milliseconds, they can equate that to a 1% drop in sales, which is, for Amazon, a substantial amount of money per day. 1% drop in sales for my website is probably like £5, But for them, it's an awful lot of money. So the bigger the deal you're taking, bigger amount of money which is coming through, bigger amount of users, obviously the more important performance potentially is for you.
Would you say, from a performance point of view, would this statement be true that things like these tag managers that people are used for marketing people and they inject JavaScript?
Yeah.
What you were saying about having to redo the DOM, would you say that's really bad for performance?
Potentially. This is really where it gets interesting performance, because if you're new to performance, you might go, oh, that's terrible, or practice is horrible, don't do it. And what really you should try and do is say, well, this is my application. I'm not Google, I'm not Amazon. How does that affect my real-world performance of my application? Does it really affect the hot paths in my application? Does it really affect my users? Because you can burn an awful lot of cycles getting your application performant and then find out it makes absolutely no difference to your bottom line. So what you need to try and figure out is where is your application slow, and more importantly, how does that impact your customers? But it brings us to the question, well, where to optimize? How do you figure out from your website, well, what am I going to change? What am I going to improve? Because there's a ton of information in that, and it's really complicated to learn any of that stuff and know any of that stuff. But it's important to know, well, your front end is really important in this. The browser aspect of it, 80% of the traffic or sort of computational stuff is happening on the front end of a web application. So you should have a focus on the application. Of course, the back end is still important, and it's very important when it comes to network latencies and bandwidth, network and response times and things like that. But the majority of work that a browser's doing, it's doing on the front end, and that's really obviously where we should start thinking about how we can improve it. So there's a few tools which you can use. One's called Web Dev Checklist, which is built by one of my friends, actually. And it's quite focused on ASP.NET, but it should be useful for anyone, whatever platform you're using. And it kind of goes through the things that you should think about when you're developing your website. And it's a checklist. Once you're about to go to production of your website, have you thought about this? Have you thought about that? And it's literally a checklist that you can type in and work through and see, yeah, OK, I need to do this, I need to do that. And that's just like a checklist, which also then tells you some information about why that's important. It's a bit of an educational tool as well. There's also tools from companies like Yahoo, like Yahoo YSlow, and Google's Page Speed Insights, which are built into their development tools. So if we have a quick look at those. This guy was taking a picture of my slides. So have a look at YSlow and PageSpeed. So this is a website that someone at Microsoft in the marketing team built. Wasn't me. And we go into YSlow. It's like an add-in to Chrome. And basically, you can say, well, run tests over my website. And what YSlow does is it tries to figure out what's slow about your website. And it's not completely accurate, but it will give you a grade of your website. So this grade performs C. And then it quite usefully tells you the things that are kind of wrong in a performance sense for your website. So you need to make fewer HTTP requests there, which is a level E. It's highly impacting your application performance. Reduce the number of JavaScript things. You need to add expire headers onto some of your content because they're not able to be cached, because anything without an expires content will not be able to cache because it doesn't know when it expires. These things aren't being compressed with gzip. Put your CSS at the top of your page. That's something which they're doing. Putting your JavaScript at the bottom of the page. That's something that they're doing. And these are all important because of that pipeline. And you don't necessarily need to understand why, but that's important, that all of these rules are made in the science of building browsers. And this then gives you an information about where your requests are, the size of your requests, what's taking up the consumption of your application, how big are they on disk in kilobytes. And then it shows you how fast your site loads with an empty cache, and then if the cache is primed, so a subsequent visit to a website, what the website looks like and how fast it will load and the actual weight that it adds. So there's two tools which are really great as a starting point to figure out, well, where is my application slow? And if you, and this is the Google Page Speed version. We say start analyzing the site, and it's the same sort of principle, and it just analyzes things differently and has a different take on it. What's probably important about this is that performance affects your SEO rankings as well. Google use page speed and performance as a ranking mechanism. So making sure that you work probably well in the Google one, I would imagine, would equate to being good for whatever they use to determine how fast your site works. And it's good because it's the same sort of content, same sort of information, It shows you what needs to be done, what needs to be changed, what you've already done to improve performance. But both those three tools, YSload, PageSpeed inside of Google tools, and the Yahoo and the Web Dev Checklist are really good things to, if you're brand new to this, as a way of understanding how you should improve the speed of your application. Some of the tools that I'll use next when we're looking at stuff are built inside of Windows. So this isn't going to be working if you're in Macs, obviously, but they have equivalent tools, I'm sure, for Macs. There's a thing called event tracing for Windows, and this is used for every application in terms of performance. So we use this to try and determine, this is the subset, the low-level Windows APIs that we use to build tools on top of. Anyone can actually build a tool on event tracing for Windows, but we build two tools. And it logs events, it gives insights to the platform performance, the CPU, the memory usage, and all that sort of stuff, and it traces the CPU over time. And then we develop two tools over the top of this. One is the F12 developer tools. So when you press F12 inside of IE, we build on top of ETA, this system. And then the other one is Windows Performance Toolkit, which is very useful if you want to see not just the browser threads, but also the threads on the entire operating system. It's probably more used, Web Performance Toolkit, by people which are actually building applications which interact with each other, not necessarily browser applications. But it's bear in mind that they both exist. We have this one tool inside of IE DevTools, which no other browser has, called UI responsiveness. And it's really trying to give you an insight into how your actual page is performing over time, and looking at all of the different subsystems in the operating system. And so we look at loading, scripting, garbage collection, styling, rendering, and image decoding, which are the six main things that your browser's doing inside of the UI thread. And we will look over, like a CPU trace, we'll trace your website as you're using it, interacting with it, and you'll see bottlenecks based upon the colors, it will tell you where the CPU is at. So there's a bit of red here, which means it's doing scripting. There's some orange, which means it's doing garbage collection. So you can figure out what the website's doing at specific points. You can also instrument this. So you could put a marker when you load from the database, or you load from cache, or you load from Redis, or you do whatever you do in your JavaScript. You could put a pointer in here so that you could see the CPU time and then see what you were doing at those times as well. You can instrument it using a W3 standard for that. And it gives you a view of all the timelines, all the functions, all the subsystems that are running, and shows you exactly what's happening. It also shows you a visual throughput. There's this magical 60 frames per second that everyone wants to get to. And this shows you how close to that 60 frames per second you are. And you'll see in this mark, we have like a bit where it drops to 0 frames per second, where we're doing a load of image decoding. So that would be an area you'd be focusing in on, going, well, what's the problem with my image decoding here? So let's look at a few problems, and I'm going to whiz through these really, really quickly. But a really common convention is use the right size images, and this isn't really very popular at the moment because lots of people are not serving the right size image because of trying to scale to retina screens or high pixel density screens. As my Surface is a high pixel density screen, I assume this MacBook Air is a retina. And so often a web developer will serve a much larger image and then have the browser resize it. And that means that retina screens get this lovely big image, and other screens get a scaled down version of the big image. It looks crisp on both. So from a design perspective, it looks fantastic. But you've got to remember, someone has to resize that image. And that happens on the CPU or the GPU of a system. So it's really a big, huge performance hit. So here we can see two traces, one from an application, which is using the wrong size images, and one which is using the right sized images. So one which is kind of serving much larger, and then they're scaling. And you'll see at the top here, the top trace, just from a point of view for the time, it's taking nearly 2 seconds to load this website. And just by using the right side images, we're getting down to 625 milliseconds, so nearly a quarter of the time taken just by using the right sized images. You see a sea of blue? That sea of blue is image decoding. So what's happening is we're serving really big images, and there's a ton of, never mind the net requests to getting those larger images, just the image decoding on the CPU, which is happening, is huge. It's a real big cost. You see there's hardly any CPU dedicated to image decoding. So using the right size images is really helpful. And that will become easier when we start seeing this picture standard coming out, rather than having to use these workarounds to get retina screens working. Reducing the number of downloads and sprites. So basically taking your application, your CSS, or your, and bundling them together. your JavaScript and bundling together into a single file, so to reduce the number of files that you actually download, the number of HTTP requests that you make. And potentially, if you're using images, creating a thing called a sprite sheet for your images, rather than loading 60 images, load one much bigger image, which is a sprite sheet, and then use CSS to kind of show the correct sprite. So sprite sheets are a great way of reducing the number of downloads in your application. But think about how many network requests you're making and try and make them smaller. Using a CDN is really important. So this is an example if you're making a request from the East Coast without a CDN, it takes 1,353 milliseconds, and then using a CDN, it's 656 milliseconds. Because a CDN, a content delivery network, puts the information closer to the user, which reduces latency. And so using a CDN will massively improve performance. So as an example, I put something into Azure, our cloud computing system, put it in storage called azure.jpg. Azure.jpg and Beeby outside.jpg. They're two JPEG images. I put them up into Azure storage. And then I went onto Azure and created a CDN for that content, which then distributes it across the world, that content, and saves it locally, basically, in data centers across the world, so that when I access it then from my hometown in Northampton, I'll have one website which has got loading it from the blob storage directly, and one which is loading it from a CDN, same image but loaded from two different places. And then I do a network trace inside of F12 tools of how long it takes to load that page. And you'll see that from the storage site, it takes 78 milliseconds. From the CDN, it takes 47 milliseconds. So if you're using a CDN, you can practically half the kind of the load speeds of your images. Lots of companies offer CDNs and so forth. Another one is to defer script execution. Make sure that you're putting your scripts, JavaScript, at the bottom of the page. And it's important because if JavaScript's in your head of your application, because of the contracts in a browser, we can't do anything till we've downloaded and processed that JavaScript. We can't move any further down. No browser can. If it requests a JavaScript file, because it can interact with the DOM, and because it could affect the DOM, we have a contract, part as the W3C specification, which says we can't move anywhere further until we've downloaded the entirety of that JavaScript, failed to download it, or unprocessed it all. So if your JavaScript application, if some things can't be moved from the head, like analytics sometimes, but anything you can, put them in the base, in the bottom of your application, or use async and defer keywords on the script tags that you use, and it defers or makes it asynchronous. But probably the best is still actually just putting it at the bottom of your application, because it won't stop the content loading if it does block. Another thing is to reduce the number of frameworks, and this is quite important, because a lot of people use Bootstrap, they'll use jQuery, Kendo UI, and then they'll say, also, I need another framework. I need a jQuery UI to do this particular spinner, and then I need another framework. And they add all these frameworks, which actually probably have, one framework probably has the features, but they maybe don't know about that feature. And so they use lots of different competing frameworks in one application, and then you get this kind of trace. And what this trace means is, if you've got many frameworks versus one framework, you see the top screen has orange. Orange stands for garbage collection. And what's happening is that those JavaScript frameworks are loading into memory. And then when they're loading into memory, because there's 16 of them and they compete for resources and they sometimes overwrite things and interact with things in different funny ways, garbage collection has to click in and clean up the memory of those frameworks. So the consequence is, because it's using lots of different memory, lots of different things, and they're interacting with each other in weird ways, garbage collection is constantly running in this example where I'm using actually 16 frameworks at a time to amplify the point. But it means that the site is slowed from 617 seconds to 35 milliseconds when I only use one single framework. So try and choose a framework, be it jQuery, be it MooTools, be it Kendo, whatever, and standardize on that, rather than having many, many, many different interactive frameworks, which perhaps you don't use all of anyway. Use CSS animations. I'm not going to explain any of this because I'm running out of time. Minify your JavaScript and CSS. Make sure that everything has expires headers on your content, so that it has a date when it expires, because without it, your browser can't cache it. Use icons where possible instead of images. Icon fonts are really good because they're scalable, they're vector-based, and you can use these for logos and things like that, and they will scale really nicely on Retina screens, but they don't have the same problems that image decoding has. Font Awesome is an awesome version of this. And then lastly, I'll leave you this, use JPEGs where possible over PNGs. And this is quite controversial because everyone goes, well, what difference does it make? But PNGs have an extra channel on them for starters because they have alpha. And sometimes you'll be using an image that doesn't need an extra channel. So don't use it if you don't need an extra channel. Use a JPEG. Here we have a website. One is built in JPEGs. And we've got a snapshot of it, and it's about 8.69 megabytes of images. That's with PNGs. And then if we just use JPEGs, we reduce the image footprint to 3.59 megabytes, so half the image thing of the application. And you may be thinking, well, how does that work? If you look at an image, it's got a color space of RGBA is a PNG. So you might say, well, on disk, it's 5.57 kilobytes. That's how much memory it uses. But in reality, we have to load those 4 channels up in memory. So it's basically, once it's decoded into the browser, on the heap, we have 2.67 megabytes of image decoded. So the more images you have on your site, don't just think it's the number on disk that's important. It's also what it looks like when it's been decoded and it's in memory, because that's what your computer has to use and work with. I won't go through the decoding pipeline. But just to say that it's really important making sure that you use JPEGs where you can over PNGs, and there's tons of really good science as to why that is. But you'll have to trust me on that because I've run out of time. My name's Martin Beeby. I work for Microsoft. I'm the Beebs on Twitter. Thank you very much.